Okay, in this video we're going to derive the spectral density for white noise, and we'll see that this derivation is going to be a very easy one, but the takeaways are really important because white noise is such an important topic, important concept throughout time series and throughout the rest of our book, so it's going to be good to derive this. Now, where we'll start is the formula for the spectral density. So the general formula is given by S sub x of f equals 1 plus 2 times this sum of k equals 1 to infinity of the autocorrelations rho sub k times cosine of 2 pi fk, where f is ranging from negative 0.5 to positive 0.5. Now, that's a big formula. It's complex. And when trying to calculate that in practice, we're going to definitely use our R software to help us do that. We'll get into that later on. But for this particular video, we're concerned with the spectral density for white noise only. And that's going to simplify the calculation considerably because of the fact of how white noise is defined. Remember that for white noise, rho sub 0 is 1, which is true for all cases, because remember the autocorrelation for lag k equals 0 is always 1. But for white noise, it turns out that for any other lag, that is when k is not equal to 0, the autocorrelation is equal to 0. So the good news is that rho sub k of 0 gets put into this formula, into this sum, so our rho of k is 0 through all of these terms in the sum, and that means we're adding up a bunch of zeros. So that means that we can say then that the spectral density for white noise is 1 plus 2 times the summation of k equals 1 to infinity of a bunch of zeros, which is 1 plus 2 times 0, which is 1. So this says then that the spectral density for white noise is always equal to the constant 1. Now let's plot this. We can learn some things from the plot. And our horizontal axis will be f. Vertical axis will be the spectral density, S sub x of f. And we've said here that our f ranges from negative 0.5 to positive 0.5. So we will make this 0.25, 0.5, and do the same thing going over to the negative side. And then for our vertical axis, we'll let that be 0.5, 1, and 1.5. But remember that we know that our spectral density is always equal to 1 for white noise. So that means that it will be a horizontal line at 1. And our spectral density looks like a rectangle. Since it's a rectangle, we can easily calculate the area. We know area is base times height, so the area of the rectangle is equal to 1. And that is consistent with the fact that we know that the area of all density curves is equal to 1. So that looks good. Another thing that we should remember is that spectral densities are symmetric. We've seen the property that S sub x of f equals S sub x of negative f. And we can certainly tell by this picture that we have this symmetry because the plot on the left side of the vertical axis looks just like the plot on the right side of the vertical axis. And for this reason, what we do going forward on our spectral density plots is we only plot the positive side, the positive f's. That is from 0 to 0.5. This left side we don't show. So that's important to realize going forward. And here's the takeaway. all frequencies are equally present in white noise. And that's indicated by the constant spectrum. And another way to look at this is that among this frequency band, there's not one frequency that has an advantage over the other. And these properties are going to be important for us later as we go on, because a lot of times we'll want to determine whether or not a certain series is white noise. And one way to confirm that is to look at the spectral density and see if we see that it is very nearly 1 at all times. And if it is, that's an indication that the series actually is white noise.